Sorry. Um, and so you might have an MPC problem which tries to track those waypoints while satisfying the constraints, and which then gives you the final optimal trajectories, which you can then try to track, or the commands can then be sent to a robot to execute those commands. And in some cases, these optimization layers are smooth and differentiable. And there was this line of work from Zico's lab, from Brandon, Priya, and a bunch of folks, which sort of showed that in a lot of these cases, you can differentiate through these problems, integrate them into standard autodiff deep learning libraries, and so plug these in just as another layer within the deep network. And one of the surprise, one might imagine, given how popular optimization problems themselves are in a bunch of applications, this setup might be widely adopted in the field. And but what we observe is that there are some issues that you face when you just try to plug in an optimization layer as is in a differentiable pipeline, and which sort of has resulted in lackluster adoption. And in this thesis, we'll be looking at some of the problems that we face when we try to add these optimization layers in differentiable deep learning pipelines. And to start with, we look at certain inference inefficiencies, which arise when you have these optimization problems as an input to the network, or when the network is a function of the optimization it fits. And we'll see that there's some redundant computation that you do when you sort of try to infer do a forward pass over the network for each of those optimization iterations. And we'll observe that even if you're able to sort of minimize or mitigate some of these inference issues, have efficient inference, you'll still have issues with training. You'll have high variance gradients, you'll have training instability, and we look at some of the underlying causes for these and try to perhaps propose some solutions to minimize these variance issues. And finally, even if you do manage to train reasonably well, mitigate some of these variance issues, we'll observe that a lot of these optimization problems have certain modeling inaccuracies or modeling assumptions about the world, which result in biases in the training procedure, which sort of result in suboptimal performance, even if you do manage to train them well. And finally, we'll look at some representational issues in these problems, which fundamentally result from the fact that the optimization problem itself is an implicit layer and hence inherently iterative, whereas the network and the rest of the operations in the network are explicit operations. And there's a fundamental incompatibility between these, which results in certain representational issues. And so we look at one paper for each of these problems. And finally, for the final representational issues, we look at a couple of proposed line of work to investigate some of these issues and perhaps some solutions. And so coming to the first line of work, as we discussed, we sort of specifically here be looking at input optimization problems in the context of equilibrium models and look at some inference inefficiencies that prop up when you try to solve these problems. And so to take a little bit of a detour to give some background, we'll specifically be looking at equilibrium models, which are essentially a class of implicit models that were recently introduced by Xiaoji, Zico, and Ladlin. And what we do here is instead of having a sequence of layers stacked on top of each other to form deep architectures, as with conventional deep networks, we instead parameterize the network using a single layer f theta, and where the output of the network is instead a solution to a fixed point problem on the layer f theta. And so given some input x, you sort of repeatedly apply the layer f theta to reach a fixed point on z star, which ends up being the output for your network. And we'll specifically be looking at input optimization problems here, where let's say you're trying to optimize over some inputs x for some network g of theta, where you have some objective L at the output of the network that you're trying to minimize. You see these problems crop up in a bunch of different scenarios. For example, you might have latent space optimization problems, where let's say you have a generator g theta, mapping from some latent space to the outputs or the data space. And you might want to try to minimize this optimization problem, which is trying to find the closest data point to y on the generator manifold. And likewise, you might have the problem of computing adversarial examples, where you're trying to find the worst case perturbation on the inputs within some epsilon ball to maximize certain objective to find an adversarial example. And likewise, you might have gradient-based meta-learning problems where, given a few short examples, you might want to optimize over some task-specific parameters to fit to that specific task, given a distribution of tasks. And across these problems, one of the things you'll notice is that the optimization iterates across that optimization problem are going to be fairly similar. And so doing a full forward pass on the network for each of those iterates is going to be inefficient. And so the problem that we're going to be trying to tackle here is to ask whether we can reuse some of the computation across those consecutive iterates. And so coming to the optimization problem itself, you might have an input optimization problem as we described earlier. And the standard way to sort of solve this problem is, let's say, do gradient descent on the inputs or some first order optimizer on the inputs, where you sort of repeat these two steps, doing a forward pass over the network to get the outputs of the network, and then evaluating the objective, doing a gradient descent step on the inputs after that. And then you repeat this until you reach a convergence on the inputs X. And as we discussed earlier, we'll specifically be looking at this in the context of the network G theta being parameterized as an equilibrium model. And so the outputs of the network G theta are now a fixed point on your layer F theta. And so that can now be represented as a constraint in this optimization problem, where the optimization itself ends up being on the variables, on the fixed point of the layer. And so now, instead of just doing standard inference over network, you're essentially solving a fixed point over the network outputs when you're computing to compute the output of the network. And then you compute a gradient through this fixed point iteration to compute the gradients for the gradient descent steps. As you might imagine, this involves two fixed point iterations, one on the network outputs themselves, and the second on the gradient descent steps as you try to perform your updates on X. And this, of course, would be extremely slow because you're essentially having to solve two looped fixed point iterations for each example. And this sort of goes back to the earlier point we were trying to make, which is that the fixed point iterations are probably somewhat redundant, given that the inputs X across these optimization iterations are fairly similar. And you might want to reuse some of the computation across the outer iterations in order to be able to use the computation more efficiently. And what that looks like is, instead of performing those two fixed point iterations as a bi-level problem, we can instead solve a single fixed point iteration, which means you only have to loop over a single optimization or a single solve. And you can define that the fixed point iteration over a joint set of variables on both the network outputs as well as the gradient descent steps on the inputs. And what this looks like is something like this, where now you have a joint fixed point operator over both the network as well as the gradient descent steps on the outputs, on the output variable Z and the input variables X. And in fact, this essentially looks like another equilibrium model where you have a larger fixed point operator which concatenates both of these operations. There are certain nuances here which I sort of skipped over, which is that the gradient operation here itself is somewhat complicated and involves a fixed point iteration to compute the gradient. And at this point, you might sort of guess what I'm going to say here. Instead of solving this fixed point separately to compute the gradients, we can sort of just plug that into our joint fixed point problem and compute those three fixed points jointly. In fact, if you just rearrange the terms slightly, what we find is that we essentially get back the KKT optimality conditions for the original optimization problem that we had earlier. And what this suggests is that if you manage to converge on your fixed point iteration, you're likely to reach a point which is going to be the optima for the optimization problem that we defined earlier. In fact, however, one thing to note here is, in fact, that's something Zach pointed out when I was giving one of the practice talks, which is a more standard optimization person might go about it the other way around, where you might define the optimization problem first, write out the KKT conditions, and then directly try to solve it. There's some nuances there in that, especially when we have a nonlinear problem or a non-convex problem, as we have here, it's more tricky to directly solve the KKT conditions or directly solve the KKT conditions using some root finding problem, given that you might get stuck in local maximas or some saddle points. And so formulating the problem specifically as a minimization problem, as we did earlier, and specifically as a fixed point iteration over that minimization problem, does ensure that you would reach a minima instead of some local saddles or local maximas. And in fact, if you do this instead of solving it using Adam or another first order optimizers we talked about earlier, you get some about 4 to 5x speedups, where here the green and blue curves are our model with a couple of different, our optimizer with a couple of different models. And you have Adam as the other two, where you see about 4 to 5x speedups when we use this optimizer against Adam. And the resulting speedups sort of now allow us to train a model with this joint optimization procedure as the inner loop within the training problem, where the outer problem here might be some objective on some training examples, and the inner problem, which is expressed as the constraint here, would be the joint optimization problem that we just described. And going back to the examples that we had earlier, so for example, if you have some generative modeling or inverse problems, these objectives would look like least squares objectives on either the corrupted input or the corrupted output or the ground truth outputs. Likewise, for adversarial examples, these would look like cross entropy losses in the outer objective, and the negative of the cross entropy loss in the inner objective. And for meta learning, this would again be some regularized cross entropy objective on the training and text examples. And we look at some of the results in all of these three settings. And to start with, this was a smallish model we trained for the generative modeling tasks with this training procedure. And we sort of get similar results to a similarly sized explicit model as well. But the thing to note here is that, again, as we were discussing earlier, if you use the joint optimizer that we talked about, you get about 3.5 to 9x speedups, depending on the number of iterations that you do solve on the optimization problem. And likewise, for adversarial training, where you use the R procedure to compute the adversarial examples and then train the models for those adversarial examples, you again observe about 3x speedups if you use this joint inference procedure instead of just simply using projected gradient descent, while getting similar robust and clean accuracies as just doing the projected gradient optimization problem. Likewise, for meta learning, we get similar accuracies to, for example, the baselines on some standard meta learning classification tasks, while again getting about 3x speedups if you use the joint optimizer instead of gradient descent for the meta learning problem. And so that sort of wraps up this line of work. And hopefully the takeaway that you got here is that especially when you have these optimization problems as inputs to a network, or if you're optimizing over the inputs to a network, you have certain inference inefficiencies that crop up when you're trying to infer your network outputs for each of those optimization iterates. And so in those cases, you might want to reuse some of the inference computation to ensure that you're more efficiently performing solving the optimization problem. Specifically in the context of equilibrium models, we showed that you can use ADMM-style decomposition to get about 3 to 5x speedups on the optimization problem. One thing that I did sort of brush aside was that when we actually tried to train these models in some of these settings, the training was extremely slow, and we had to use a bunch of tricks to sort of stabilize the training as well. And that sort of takes us to the second part of the talk, where we'll sort of look at the reasons for some of these training instabilities when you try to add these optimization problems within these learning pipelines. But instead, we look at it in a slightly different setting where you can sort of decompose the optimization problem and the network inference itself. But before we go any further, do we have any questions? All right. So for the second part of the talk, we'll sort of be looking at these issues of training instability and speed when you try to add these optimization problems within deep network pipeline. And specifically, the problem that we'll be looking at is an increase in variance when you try to add these optimization layers within inference problems. And we'll be looking at it specifically in the context of bundle adjustment layers, which are, again, very useful across a bunch of robotics applications. For example, you might have SLAM or visual odometry, where you're trying to reconstruct the scene while estimating some camera poses, given some image observations. You might have structure for motion, like 6D object pose estimation, where across these tasks, you have these bundle adjustment problems, where you'll have a sequence of frames. And across those frames, you might have certain correspondences that you might have estimated for, or correspondences or flows that you might have estimated across those frames, and the corresponding weights or confidence weights for those correspondences. So in the example that we show here, blue lines sort of indicate high confidence correspondences, whereas the orange and red lines show low confidence correspondences. And so for a bundle adjustment problem, you give these two things as input to the problem. Then you solve a nonlinear least squares optimization problem to solve for the poses and depths for the camera and the detected points. And the optimization problem itself looks like this nonlinear least squares problem over the poses and depths, where you try to minimize the reprojection error across these frames. And once you solve the problem, once you get an output, you can sort of have an objective on the output of the bundle adjustment layer, something like on the flow of the resulting reprojected points or on the poses of the frames using ground truth poses or ground truth flows that we might have for the dataset. And specifically, we'll be looking at one recent paper which used a pipeline like this called DPBO, where we have a neural net taking these observations as input, predicting these confidences and correspondences or flows across frames, feeding it to a bundle adjustment layer to predict poses and depths, which are then used using, and then we use the losses that you saw earlier to differentiate through this pipeline to learn the network parameters. And so if you just, for example, plot the validation errors or validation ATEs across training for this model, you observe that the training is actually very unstable, and it's also very slow compared to, for example, what you would expect with some of the modifications which we'll talk about in a little bit. And in fact, if you also try to plot the signal to noise ratio of the gradients for these models, you'll observe that the signal to noise ratio is much lower than what you might hope for. And what this suggests is that the gradient variance for these problems across training is probably too high. And so what we'll be doing in this work is trying to figure out where this gradient variance comes from, and maybe try to propose some solutions to mitigate this gradient variance. Specifically, we identified 3 causes for the gradient variance in bundle adjustment layers. And what we find is that fundamentally, all of these 3 reasons or causes arise from the fact that as opposed to standard deep layers, you have certain multiplicative and inverse operations in bundle adjustment layers and optimization layers more broadly, which result in any variance in the variables also transferring to a variance in the gradients themselves because of the multiplicative interactions. And as opposed to standard deep layers, where you might sort of plug in some normalization layers or skip connections to mitigate some of the variance, you can't quite do that here, given that the variables here are have some grounded meaning, and can't just be arbitrarily manipulated to reduce the variance. And so the first set of tools that we sort of looked at to reduce this variance was to sort of use the fact that we do have access to some ground truth variables, for example, the ground truth flows and ground truth flows, poses, etc., to sort of regularize the optimization problem to reduce the variance in the variables themselves. But what we observe when we try to use some of these approaches is that that leads to some additional bias in the optimization problem, which again, in some cases results in its own sets of instabilities, or in some of these other cases, certain additional bias or saturation and losses towards the end of training. And so it's sort of important to sort of pick the right priors when we're trying to, especially when you're dealing with these grounded variables. And so going back to the drawing board, one of the things we sort of observe, which is sort of standard in a bunch of these 3D reconstruction type problems, is that most of the variance here actually comes from the fact that you have outliers in the problem, and the outliers contribute to a large fraction of the variance in the problem or in the variables. And they are indeed the reason for the variance in all of these three issues that we discussed earlier. And in fact, for the inner problem, we do use some notion of confidence to weigh the outliers out, to sort of reduce some of the variance in the inner problem. But we don't do anything of the sort for the outer problem when we compute the objective for the flows in the loss itself. And so we tried a few different heuristics to reduce the variance or to reject outliers in the outer objective. But as it turns out, a much more simpler approach where we just use the confidences predicted by the network to also weigh the flow objective in the loss works exceeding much better than most of the heuristics we tried. And what this suggests, and in fact, what we also observe, is that the network, in some sense, learns these confidences much faster than it learns the correspondences themselves, because the outlier detection problem tends to be a much simpler problem than predicting the correspondences or the flows themselves. And so with this simple modification, again, I've sort of spoiled some of the results here, but we get much more stable training, much higher signal to noise ratios, and faster training as well. And in fact, a lot of the method sort of trivially transfers to a bunch of other settings. For example, the first plot here shows a global optimization problem instead of the streaming problem earlier for pose estimation. And the second one here is a dense SLAM method, which is again fairly famous in the SLAM literature. The benefits also transfer to the generalization accuracies, where here we show the generalization errors on the Tartan test set, and we observe significant benefits with the modifications that we proposed. Interestingly, the benefits don't quite transfer to out-of-distribution generalization, mostly from the fact that most of the errors there arise from the sim to real transfer, and so there's not much that can be done by reducing variance for those problems. We also apply some of these things to a visual aerometry problem for satellites. Specifically, we're looking at the lost in space problem here, where you have a satellite with only access to a camera and an IMU launched in space, trying to localize itself in orbit. And the main difference in the bundle adjustment problem here, as opposed to what we described earlier, is that here, on top of reprojection error, we also enforce consistency on the dynamics of the problem, given that we have access to accurate dynamics for the satellite. And we observe that with those small modifications, we get significant benefits over, let's say, something like a ground radar. We're able to localize within to about 5 kilometers of position accuracies within 6 hours of deployment. This is, again, to add some caveats, within a simulator of the system hasn't yet actually been deployed on the satellite itself. And this was, again, work led by Kyle, who is one of the PhD students in our lab. And so that sort of wraps up this line of work. And hopefully the takeaway that you go with here is that bundle adjustment layers and optimization layers more broadly often have high variance in gradients, mostly resulting from the fact that you have multiplicative operations between variables, which results in variance in the variables themselves getting transferred to a variance in the gradients. And with the right set of design decisions, you can sort of hope to reduce some of this variance. But you need to be a little bit careful about making those design decisions because often they also result in biases. And having said that, there are still fundamental issues regarding model inaccuracies that arise either in the optimization problem or the simulator that you're using to solve the problem, which result in suboptimal performance or weak generalization for the final model. And in fact, that gets us to the third line of work, where we'll be looking at ways to sort of handle these issues with approximate dynamics or approximate modeling error or approximation errors in the model as we try to incorporate these layers within differentiable pipelines. But before we go there, any questions, clarification questions on this piece of work? All right. So for this piece of work, we'll be looking at a setup like this, where if you have, for example, modeling inaccuracies or modeling biases in the layer or the optimization problem you're looking at, we might have issues, as we discussed earlier, of the training itself getting biased due to those modeling inaccuracies. And we'll be looking at ways to sort of still use the model information, but at the same time, figure out ways to sort of reduce some of the biases that creep in. And specifically, we'll be looking at it in the context of sim to real transfer. So for example, if you have a system like this, where you're trying to learn a controller for a real system, you might imagine just running a reinforcement learning algorithm to learn the controller, but that, of course, is somewhat sample inefficient if you have to collect samples from the real robot. And the specific question we ask here is, let's say, if you have some approximate model of the real world, especially if it's differentiable, if we have some way of exploiting the model to sort of make the learning more sample efficient. And in fact, there is a line of work in the optimal control community, which says that you can still use your real system to evaluate the policy, but use the Jacobians of this approximate model to speed up training and to make the training more sample efficient. In that context, of course, it's not quite in the context of training, but optimizing optimal controllers for the policy. And so what that looks like in the ILC setting is, for example, if you have the control problem that we described earlier, expressed as some quadratic costs with some linear constraints, with the dynamics Jacobian baked into the linear constraints, we, of course, don't have access to these system Jacobians for the real system. And so what ILC says is, instead of using the true dynamics or true system Jacobians, you should instead substitute the model Jacobians or the approximate model Jacobians that you might have while solving the optimization problem. And so the caveat here is that you're still using the true system to evaluate your policy. And so you're doing the forward passes on the dynamics on the true system. But then when you're trying to compute updates on your state or actions, the backward pass on your dynamics or the Jacobians of the dynamics are evaluated using your approximate model. But then this problem, again, is only feasible if the problem you're looking at is fairly repeatable and deterministic. And so what we'd want to do is sort of generalize this insight that we get from ILC to more broader class of policy learning problems, for example, within reinforcement learning, to generalize to a broader class of tasks. And so, look, the specific contribution we make here is to propose the value gradient update. And what we say here is that instead of simply enforcing a consistency on the value function across time steps, which we do with, for example, the Bellman error, or minimizing the Bellman residual across the Q function, the current time step, and some rolled out Q function, we argue that you should also be enforcing consistency on the value gradients across these two Q functions. You should also be enforcing value gradient consistency across these time steps. And what that looks like is essentially differentiating your Bellman updates with respect to your initial state action pairs for both the unrolled computation graph and the non-unrolled computation graph, and matching those two gradients. And that looks something like this. As you might see here, you have dynamics Jacobians appearing on the right-hand side, which, as you might have guessed at this point, we can sort of naively substitute with the approximate model Jacobians that we might be able to evaluate using the simulator, while still evaluating the policies and getting the observations from the real system itself. And the nice thing here with an update like this is that you can sort of plug this in to any arbitrary off-policy or on-policy reinforcement learning algorithm. And it's also fairly flexible to stochastic problems, can be used with neural net policies to learn arbitrary controllers. In fact, even if, for example, the dynamics is ill-conditioned or is non-nice in certain ways, you can sort of, because this update sort of only backpropagate or only needs to be backpropagated through a single time step, it's sort of much more robust to these kinds of gradient explosion and vanishing problems that you might face with something like ILC, or trying to unroll things, or trying to unroll the gradients through multiple time steps. And interestingly, what we also find is that if you look at the original optimal control problem that we had earlier, the dual updates of the problem actually look very similar to the value gradient update that we just proposed. And what that suggests is that the value gradient update we proposed is essentially just an amortized dual update for the underlying optimal control problem. There are, of course, some nuances here, in that the dual update here is on the value function v, and the update we proposed earlier was on the q function q, but I'll leave out those details. And a lot of these modifications can be like very straightforwardly applied to some practical algorithms. For example, if you here we modify soft actor critic, where you might have the standard TD learning or like standard TD objective for the Q function, and all that you need to do to get the value gradient update is compute a gradient of some typos that was supposed to be the residual instead of the entire objective. Pardon me for that. But essentially, if you can compute the value gradient objective by just computing the gradient of the TD residual and then taking a norm and plugging it into the Q learning objective, and everything else in the algorithm remains about the same. And if you essentially just perform those modifications and try it in the task we had earlier, where we tried to train the policies from scratch on, let's say, a system with significantly different dynamics, you observe that with value gradient updates, you get significant speedups across a huge range of tasks, including certain problems with contacts. In fact, even if you don't have access to gradients, or even if the simulator itself is non-differentiable, you can compute finite difference Jacobians on the approximate simulator you might have, and use those to perform updates on your policy and value functions and get similar speedups. And finally, instead of training your policies from scratch, if you're trying to fine-tune the policy in the transfer system by pre-training it first on the original simulator you might have had, here again, we have 4 different settings here, where the pre-training itself can use the value gradient updates or be done with RL, and the fine-tuning itself can be done with value gradient or RL. What we observe, of course, as we did earlier, is that if we use the value gradient updates for the fine-tuning, you do get faster convergence, etc. But what you also observe is that if you use value gradients for training or pre-training, regardless of the algorithm that you use for fine-tuning, you get faster transfers, which is interesting because there are some biases that are being that are useful here, which are not just, which is interesting. And so that sort of wraps up this line of work, where I hope the takeaway is that first order information, especially in a lot of these optimization problems, is useful. And even if you can't get access to true simulators or true system parameters, you can still use approximate Jacobians from approximate models you might have to accelerate your optimization problem. And we proposed a specific update in the context of sim-to-real transfer for reinforcement learning problems, which are sort of generalizable to a bunch of different policy optimization procedures. And that sort of wraps up our prior work. Any questions so far? All right. There were, we primarily presented these 3 pieces of work, but there were a few others, which I just wanted to point out. There were a couple more on trying to speed up these optimization problems or training procedures with these models in the loop, using GPUs or using parallelism. And then we had a couple of systems papers, one which we talked about briefly for the lost in space problem, and another led by John for the motion imitation problem from casual videos, which again tries to plug in a model predictive MPC problem after you get some reconstructions from videos. And finally, moving on to some proposed work, we'll specifically be looking at representational issues that crop up when you add optimization problems within differentiable pipelines. Specifically, the problems here arise from the fact that some of these operations, for example, within the optimization layer, are inherently iterative and are implicit, whereas the rest of the network tries to single shot infer the parameters theta using explicit operations. And what we'll advocate through both of those work is that to mitigate a bunch of representational issues, you should instead be looking at this inference and optimization problem as a joint problem over your parameters theta and the optimization iterates tau. And specifically, we'll be looking at it in these 2 scenarios, where for the first set of proposed work, we'll be looking at it in the context of differentiable constrained nonlinear programs, where, for example, if you have a trajectory optimization problem or model predictive control problem, specifically, let's say a trajectory tracking problem as we introduced earlier, you might have a network predicting certain waypoints for your robot to follow, given some observations, and then you might have some MPC tracking controller to track those waypoints while satisfying certain constraints. And if you just try to have a sequential procedure as we discussed earlier, there are certain problems. For example, the estimation problem for the parameters theta might be pretty hard. And trying to do that single shot might be representationally too difficult for the network. And for example, if you have problems where you could benefit from some warm starting on the optimization iterates, if you're using the network to estimate the parameters theta afresh for each new time step, the parameters might be different across or significantly different across time steps, resulting in difficulties when warm starting. And likewise, for example, if you're predicting parameters for constraints for the optimization problem, you might observe that the network might predict parameters which are completely infeasible for the optimization problem to solve, which might itself result in certain issues when you're trying to solve it online. And we observe that one of the primary issues causing or leading to all of these issues is the fact that the network is not conditioned on the solver state, and instead is trying to predict the optimization parameters single shot from the observations. And so going back to what we were saying earlier, instead of trying to have this one-shot procedure as we do, for example, with differentiable MPC and stuff like that, instead we'd like to propose tech MPC layers where instead of solving this one shot, we have this joint optimization problem over the network, over the optimization parameters theta and the trajectories tau, which we solve to convergence iteratively. But as you might imagine from our first piece of work, doing this naively and solving this optimization problem to convergence for each of those iterations might be too slow, especially to train the network. And so a lot of this work is going to be about trying to figure out how to speed things up, how to have this iterative joint optimization problem in this context, such that it's still fast enough to be trainable. And for the second piece of work, we'll have a slightly different problem, specifically mechanism design with LLM agents. And the specific problem we'll be looking at here would be in the context of systems where the agents themselves have only access to partial or private information in a multi-agent system. For example, a system like this, where you might have a population of humans with private or partial information about the system, exposing their preferences to the system to then, where the system then reaches an equilibrium given those preferences. Now, the humans might not be satisfied with the equilibrium that the system reaches, and so might want to refine their preferences given access to the equilibrium that market reaches. Unfortunately, with humans, this is somewhat difficult, given the bandwidth and time limitations that we as humans might have. However, if you have LLM agents representing those humans in these systems, you might be able to have an iterated equilibria like this, where you sort of go back and forth between exposing your preferences and based on the current market equilibrium. And so that sort of wraps up these two pieces of proposed work, which we hope to finish, let's say, by ICML and NeurIPS this coming spring, and hopefully have some job search in the middle. And the hope is that by August, we'll have finished most of that and job search, and then defend sometime around late July or August. But we'll see. Right, so that wraps up most of the work here. Thanks for listening. Any questions?
So are we gonna do committee first then?
I usually do audience first because they don't stick around with the whole committee that way, and they usually filter out slowly, even though it's technically the.
I'm for it.
All right. So yeah, questions here or online in the audience on Zoom.
Yes.
So I have a question about your proposed work. Can you go back? Right. Oh yeah, just the next one, the mechanical design. So, but do you think the preferences can be adversarial in this case? Because it seems like if you jointly try to optimize for the preferences and the equilibrium, if the preferences are adversarial, then there might be issues. Do you see yourself addressing some of these?
Yeah, I mean, I think that preferences could definitely be adversarial as well. But I think the hope in a lot of those cases is you design the game solver in a robust enough way so that those adversarial issues can be addressed. And so, for example, if you imagine something like a voting system, you might have coalitions sort of banding together to get specific outcomes, but then you might want to have a robust voting procedure to make sure that weird adversarial behavior in voting does not dominate the system. Yes.
Which does it matter what kind of optimization problem you're solving, what class it belongs to?
Right. It absolutely does matter. And I think we sort of cycled through a bunch of optimization problems. Almost, I do think that the observations were relatively general in the sense that you would have in a lot of cases problems which are optimizing over the inputs to a network. And so like I think a lot of the things that we discussed in the first piece of work is relevant, and you'll have inference inefficiencies, for example, that likewise in a lot of problems, you will have high variance in gradients. The specific problem we discussed about multiplicative and inverse operations causing the variance might be different. For example, you might have ill conditioning issues resulting in high variance in the variables themselves, which sort of also happens here, we didn't discuss. And essentially, you could have a lot of issues that result in variance, and we sort of discussed some of those issues, but I absolutely agree that I think a lot of the problems are, or a lot of the issues that you face would be very problem specific. And optimization problems are general enough that I wouldn't go far enough to sort of classify what types of problems, what types of issues you might face, and so on and so forth.
Anybody else? Going once, going twice, all right. Committee then?
Yeah, and usually we go by order of geographic distance, which I'm guessing is Fladlin. Given I have no idea where in the world he may be on any given day. Maybe you're here in Pittsburgh.
I might just be the most distant, yes.
All right.
So
Where are you?
let me ask you about visual odometry. Can you hear me?
Yeah, I can hear you.
It's a little
Okay.
quiet. Can we just try quickly plugging in the speakers
I
here?
tried it at the beginning.
Okay,
and
it doesn't work.
didn't
Okay,
work,
then
so
just
which is why I
repeat the
started.
question and that should be fine.
Sorry about that.
Great. All right. I'll speak up as much as I can.
Sorry about that.
But I suspect that the problem is not on my end.
Right. No, it is at my end. I will try to repeat the question, though, so don't worry about it.
Cool. So let me ask you about visual odometry and SLAM, because maybe that's the area that I'm most in tune with recently. So these works, Droid, SLAM, DPVO, they're very well known. You know, this guy Zach, who was an intern of mine back in the day, is just amazing.
Right.
And I guess the impression maybe in the folklore is that he kind of squeezed as much out of this problem as could be squeezed. They kind of given the data, and with these general approaches, he really did, an incredible job. And it's this, this outlier person who generated this work and kind of got as far as one can go with this paradigm. So how much do you think you can contribute? How much can you push? Can you meaningfully push sort of the performance of these systems? Did you find an aspect in these problems that you think Zach and others missed? Because kind of surely they looked at their training curves. The Zach is sort of a 10x engineer, and so what is the different perspective you think you bring here, and how much sensitivity do you think the outcome has to this perspective?
Right. So to repeat the question, Vladlin sort of, the first author in a bunch of these papers was essentially one of Vladlin's interns, and he's genuinely an amazing person. He did a lot of this work by himself. I don't know how one can do this much work in a single PhD, but he did manage to. And he sort of squeezed a lot of the performance gains that you could get from these works. In fact, I think one of my friends had a chat with him, and he used to single-handedly use most of Princeton's cluster for a lot of these problems. Vladlin's question was about how meaningful a lot of these gains actually are, given he sort of probably did squeeze out most of the benefits that you could get from these methods. And to be fair, I do think he did an insane amount of work to get very impressive results. However, I do think, especially a lot of the papers that he wrote were almost, I think they were almost trying to build a system to work incredibly well without trying to tease apart the specific contributions that each component and each of the individual design decisions made. And I think as a result, they sort of, and I should sort of also point out that the validation curves that you're looking at here are the validation trajectory errors and not the validation losses. The validation losses are somewhat nicer than this. And so the variance problems are actually much more, or do look much more pronounced in the validation errors, which they don't quite plot in the papers. But sorry, coming back to the main point of the paper, so I think a lot of the contribution here, at least in my eyes, is sort of one, to understand or tease apart some of these numerical problems that you face when you try to work with some of these optimization problems. And as a result, we sort of found one space of things which they did not consider as much, which was about the variance in these optimization layers, or variance in training as you add these optimization layers. And as we sort of showed, this variance issue was not just specific to one of their papers. This was actually common across a range of papers. And using very simple techniques that we sort of described help with most of those methods. Which just goes to show that the space is, the systems might have been built, but as with a lot of engineering disciplines, we have built the system without understanding what's happening under the hood. And some of the hope here is to sort of understand what's happening, and then maybe a little bit and propose specific solutions to address specific issues that you might be facing in those larger complicated systems. And I hope that answers your question.
Yeah, very good. Looking forward to the final results. Exciting. I can pass the baton to the next committee member.
All right, thank you. Max, do you have questions?
Sorry, yes, I do. One thing, I was very interested in the directions around LLM agents and sort of more economic applications at the end. That feels like a really kind of creative use of this toolkit. What I was a bit interested in is that in many of these kind of game theoretic settings, and maybe this was a little bit touched on in the earlier question, we don't necessarily think of ourselves as being given a fixed problem, but we rather sort of like think of ourselves as operating in some sort of online learning situation, right? And it's not really necessarily clear that in online learning, because of the non-stationarity, the aim isn't simply just to have KKT conditions, but it's actually to learn some algorithm that in addition satisfies some maybe stability guarantee, and these things together lead to what might be low regret or other notions of online performance. And so I'm wondering whether or not some of these ideas in the kind of like learning with integrated optimization can also be extended beyond situations where you're trying to get a fixed optimum, but to things where you want something that has a kind of more game theoretic, and potentially time varying non-stationary quality.
Right. That's a very good question. So the question, what Max was asking is, here we sort of talk about stationary distributions where we sort of have, or agents have an infinite amount of time given some game theoretic problem or market to reach an equilibrium to then reap the results of the equilibrium. But in a lot of cases, you'll sort of be working in a streaming setting or in an online learning setting where the distribution keeps changing, where your problem keeps evolving, and the agents sort of need to adapt to those changes in an online learning fashion, while sort of trying to make sure not just optimal performance for themselves, but also stability in the overall problem. And I think this sort of goes back to the question that I think Anurag asked earlier in the talk, and sort of related to that, in the sense that in some of these cases, even if you're looking at static problems, you might have certain agents wanting to act adversarially or trying to perturb the system to get an equilibrium that they desire, but not the rest of the population. And I would imagine the online learning setting, especially if you're looking at stability or a lot of these other properties which don't necessarily directly correlate with the performance of the system, would involve similar properties where you'll be looking at some adversarial perturbations, which each of those partial information agents might have in order to guide the system in their specific way, which might sort of destabilize the overall system. And I would imagine, at least at a surface level, that you just have to design the game solver or the optimization problem in the solver in a way which sort of ensures the problem is relatively stable.
Right.
You could
also clarify something really quickly. Yeah. So there's two senses of stability that might be getting conflated. So there's the control theoretic sense of stability where adversarial perturbations can knock the system off course.
Right.
There's also a sense of algorithmic stability, which is crucial in online learning settings. So algorithmic stability basically means that the decisions that the online algorithm makes don't change too rapidly. And this process is also necessary to achieve low regret. So if you read an analysis of, say, follow the perturbed leader, follow the regularized leader, it's this kind of per time step stability in the algorithm itself. And I do like what you said about potentially having the solver built in. And I sort of wonder whether or not loops with explicit algorithms like hedge or multiplicative weights or these sorts of like kind of classical online learning tools might work well. It's not immediately clear how one implements this, but the point is that there are algorithms that are designed that aren't simply for getting, say, small KKT error. They're designed to have these additional properties, and potentially they could be included as well. And the issue is, again, not necessarily that we want to be robust to perturbations that can mess things up, but actually ideally get low regrets or do as well as we could have possibly done in hindsight. I can imagine various techniques based on sort of the existing presentation that can get more stability against adversarial perturbation. But I think in these like online decision making processes, you want to do as well as you could have in hindsight. And maybe there are other ideas that can be incorporated.
Right, I agree. I think there was another axis which sort of I did not point out here, which is, I think, in a lot of these online applications, you sort of expect to already be in equilibrium. And when you're already in equilibrium in a lot of these applications, you probably don't even need the iterative procedure or iterative equilibrium finding procedure that we are talking about here, and which is how a lot of systems operate today, or a lot of markets operate today, where the market equilibrium is sort of assumed continuous and not changing, and so humans can have access to the equilibrium as it stands and predict or expose some preferences. The challenges that sort of come here is that the assumption there of equilibrium remaining static is somewhat not true in a lot of cases, especially as distributions or change of distribution of preferences change quite drastically. And in those cases, I think, and those are the cases where a lot of these iterated equilibria type things would be useful. And there, I guess you would also need to have some, I think the way to minimize regret in a lot of those cases would be to have some prediction over where the equilibrium is likely to go in the next few time steps with certain uncertainty bounds, and then use those predictions to predict how the preferences should look like, how the games should be solved to reach certain equilibria. I'm guessing that sort of ties back to how to regularize these problems, or how to use algorithms to make sure regret over time is minimized.
Yeah, I like that interpretation, that sort of like most of economics has to be done in equilibrium anyway, right? Otherwise, like, unless you get lucky with the Federal Reserve having a good chair, you're kind of out of luck. Anyway.
Indeed.
Just answering the questions, and I'm happy to talk more offline. I don't want to take up too many of other.
Thanks a lot. Jeff, do you want to go next?
Sure. So let's start with a very high level question. I'm trying to imagine, N months ahead, looking at your job talk and trying to figure out, like, how are you presenting yourself? Like, you're the best at X for some value of X. And so, like, I'm inferring that it's got some component of like understanding optimization well, some component of understanding equilibrium and deep equilibrium layers well, and some component of making stuff work, right? Like just getting the best possible localization error for a satellite or something. What ratio of those things, or something else, are you aiming for?
Right. Existential questions.
Yes, sorry. What is the meaning of life?
Good question. Thank you. No, I think so I would probably weigh more on the first two than the latter ones. I do think there is, like, I think being in both Zico and Zach's lab sort of does give you certain, at least access, and I think more than these specific works, I would say the exposure in those labs sort of has trained me more than the specific works I've done. And so you do get access to a bunch of optimization-y folks who have, I mean, I think that's sort of also what reflects here, where I think sort of tried to look at optimization problems in a bunch of different contexts, whether it's state estimation, optimal control, hopefully in game solving, so on and so forth. And so, like, I think partly, I think it is the ability to sort of get into a new problem, having a relatively strong set of basics, so that getting into a new problem and quickly adapting to that specific problem, as long as it involves the set of tools that I've sort of been familiar with. And I think I would say that's sort of what I've been good at more broadly.
So actual follow-up question then is, since that's the goal, can we make a thesis statement that supports that goal, right? So your thesis statement here is, here's a variety of problems, that places where things don't work, and a variety of patches that make parts of those things that don't work start to work, right? And that's not motivating to a hiring committee the way it is. So maybe something like, you know, if we look at deep nets through the knowledge of the structure of the internal optimization and through the actual problems that occur when we, you know, put the rubber against the road, we're able to, you know, improve optimization theory in a way that, I'm not liking this one, but can you, you know, so either now or like sometime over the next N months, I think this is an important question to answer.
Yeah, I definitely agree. I think part of the problem sort of comes also from the fact that I think I don't know what kinds of job places I'll be giving job talks in, given the split personalities I have in my head. And so I think the past few months have been about trying to resolve those split personalities and figuring out which of those I want to stick with. And so I think that, that's the existential, sorry about going back to the existential questions. But I think about I think the pitch, at least from what I have here, would sound more, I mean, not very dissimilar from what you were already pitching, which is
better worded.
Somewhat better worded, hopefully, which is that if you have a lot of real world problems do need optimization problems to be working in tandem with deep learning pipelines or learning pipelines. And that sort of needs certain background from the optimization literature, as well as some background exposed in the deep learning community or like the learning community more broadly. And I think like being in those two labs sort of has helped me at least go back and forth. And I would still not, I think they would agree, I would still not claim to have mastered all of it, but I think I do have a decent sense of both of those areas. And I do think there is some benefit to that, especially in a lot of these problems where you do tend to get, have to combine both.
So I think let's maybe iterate like offline on something like this. But I think in addition to a problem statement, like being able to say, like, what have you contributed in a way that makes it obvious that you're like carrying that problem forward.
Right.
Is going to be important.
Right.
I think that's true no matter, like,
that's a good point.
You know, all portions of your split personality can agree, right, on like making you look expert. Right.
Fair enough. I agree. Thank you. Yeah, let's maybe chat offline and then figure out the details.
So I have a bunch of like smaller technical questions, maybe this isn't the right forum, so maybe we can maybe we can talk again, like offline.
Of
about
course.
some of those.
That'll be great. Awesome. All right, thank you. Zach, do you want to? Yeah, of course. Yeah.
All right. So yeah, I wanted to ask, like, for me, the meta question, which is a bit more in the weeds and less existential. So I think a lot of what you've done is like building on the differentiable convex layers kind of idea. But I'm curious about this like bigger picture question of like, so you did this kind of stuff in a bunch of different contexts, and I'm looking for like some generalizable insight there. And I think one for me that I really struggle with here is like, the reason the convex layers idea makes a lot of sense is that, you know, we know everything about convex optimization problems, so we know how to solve them. There's all these nested guarantees, so it's like a very deterministic thing that, you know, in principle is just a function that you can stick in there and treat like any other function. But as soon as you go non-convex, like there's demons in there, right? And we don't even know if we can solve the problems. We can't bound the runtime. Like there's all kinds of weird crap. Like one of the things I wanted to maybe focus on, but I'll skip to later, is that like particularly in some of the deck MPC problems, like anytime you're solving a non-convex problem and you're parameterizing the functions in there, like with thetas like that, like I don't even know for some given random set of thetas that problem's feasible, like it even has a solution, right? Like that, all this kind of stuff, it could just go completely off the rails, right? So I guess my like question then is like, now that we're introducing non-convexity into these layers and there's all these demons lurking in there, like, what is the advantage of that? And where do you draw the line between like, what should I just learn versus what should I try to optimize?
Right. I think it sort of goes back to the question that I think one of the folks asked earlier. And I think my general takeaway here is that I think as far as possible, you do want to have, or you want to design your end-to-end system such that your inner optimization problem or the optimization layer itself is relatively convex. It doesn't have to be completely convex, but I think reasonably convex so that you can sort of at least expect to find some solution for the optimization problem itself. And I think then there are still issues of the outer problem still being non-convex in a lot of ways. And I think there's some simple examples which I didn't talk about, where like, even if the inner problem is relatively convex, the outer problem can still be nasty and non-convex. I think a lot of, at that point, I think it's super hard to say a general statement. I think it becomes very problem specific, which is sort of what we find in a lot of the papers as well. And I think the only thing I can probably say, which I think goes back to the deck MPC stuff, is that as far as possible, especially if you have access to data, going back, like the reason you're trying to add in optimization layers as opposed to just having an end-to-end thing trying to predict those quantities is the fact that you don't have access to certain types of data and you're trying to compensate for that using additional priors or additional domain knowledge that you're adding into the system as constraints, as objectives, so on and so forth. And so, like, if you do have access to huge amounts of data, if you don't have computational constraints, of course, please don't use optimization layers. But I think in a lot of real world applications, I think data is going to be constrained, especially in certain parts of your space. And so, for example, if going back to the differentiable MPC or the deck MPC type things, you might have demonstrations where you never violate any constraints. And so if you don't violate any constraints, it's going to be hard for your network to know that you should not be violating those constraints. And so baking in those constraints as part of your deep network is useful. And you would want to do that because the data itself does not give you information about that aspect of the problem. And so like that sort of, and so you would want to minimize the amount of priors that you want to add, especially if you can get data. But then the price that you're adding is to compensate for the lack of data in some sense, at least in my mind. And there are cases where you might get certain representational richness. For example, in the last piece of work we talk about, where instead of having just a network predicting certain quantities, having an optimization problem in the loop sort of helps you sort of decompose these tasks, where predicting the waypoints for a task might be an easier learning problem than trying to predict the controls themselves. And so I think it's a huge range of considerations. But fundamentally, I think it goes back to that point where, like, I think you're trying to, the reason you're baking in the knowledge is because there is certain missing data,
Yeah,
or like
I
certain.
think that's a beautiful point that I would have loved you to make. So I guess that's my thing. Like, I think that's a very strong argument for the whole thing. And yeah, maybe trying to infuse a bit more of the big picture, like, why are we doing this kind of stuff would be good.
Yes, that's a good point.
But I think you had a very good answer. So you try to get that in
I'll get that in.
the main body of the
Makes sense.
talk / thesis.
All right, thank you. Cool.
So maybe building on this point, I have a more general question, which has pained me for a long time, but I want your take on it. So if this is the case, that the reason to include optimization layers, you don't have enough data, you are data limited, you want to enforce priors, you want the structure of net worth to correspond to prior that's known. We have a whole lot of domains that are like this. Most robotics problems are like this. I would argue a whole lot of other sort of specialized tasks are like this. Almost no one uses optimization layers in deep networks. Why is this the case?
I think some of the problems I was talking about would be some of the reasons for those issues. But I think more broadly, I think I didn't stress what were the actual pain points. I just listed a bunch of pain points. And at least from our usage here, I do genuinely think solving the optimization problem fast has been annoying for a lot of problems, especially if those optimization problems are written in, for example, PyTorch. And for example, for a lot of these problems, the training times still take days, even for small problems, which is not ideal. And so I think, so that's one of them. I think the training issues are legitimate as well, which was the second piece of work which we were talking about. I think I sort of condensed it down to one specific problem in gradient variance, but there are a huge set of problems there, which result in issues in training. And I can go on and on about problems, but I mean, I think what I'm trying to get at is that it is fundamentally immature, as the set of methods themselves are relatively immature. And I think one of the things I am sensing here, for example, is people want me to say generalizable things about these problems, about the things that we've sort of found, but it is hard given how specific the problems are in each of those applications. And that sort of makes it, especially for someone coming in to and trying to use these optimization layers within a standard learning pipeline, sort of makes it hard to tell the person, do this and it'll work. Because the challenges are nuanced, and getting it to work is also, as a result, a nuanced problem. And so I think, in some sense, it's like the market problem we were talking about earlier, where given that deep learning with just huge amounts of data seems to be working as well as it does, maybe you don't need to worry about all of these things. And that might indeed be the case. And for example, even for the 3D reconstruction problem that we were talking about earlier, most people right now are trying to do just that was one problem where I would have imagined having bundle adjustment layers optimization problems is actually genuinely useful a couple of years back. Doesn't seem to be the case. And so it's unclear if huge amounts of data is, and I think in some sense, it's because of the fact that collecting data, or even for these tasks, is actually an easier exercise than having a few engineers crunch it, trying to figure out how to get this work. And so but I do think there are problems, for example, especially with the MPC example, where you do need safety constraints, or if you have large-scale market systems where you do want to make sure you give people some semblance of reliability in how the system is evolving. And so especially in these types of domains where you don't just want to throw your hands up and say, this might work, or this might work, but we don't know why it works. I think those types of scenarios are scenarios where you might still want optimization layers. I think that in those types of scenarios, I think it's more a question of the communities coming together and actually using it. And so, for example, if you look at L4DC or some of the conferences like that, people do tend to use optimization layers or differentiable optimization in quite a few different papers, given that they do care about safety as a prerequisite in a lot of those applications. And so I'd say, I mean, I think that's sort of the picture in my mind. I don't know how it will evolve, but maybe the safety folks also stop caring. But at least so far, I would say that's where it is in my mind.
Okay.
Can I maybe make one really small point, which is sort of combining what Vico and Zach have just said, which is that if we really think that the killer app of optimization layers is their ability to provide external guarantees or scrutability on these networks, doesn't it then seem that one of the things that maybe should be emphasized is something like convex certificates or pseudo-convex certificates, or these other things that we might be able to, like what would be the correct protocols for extracting safety guarantees from these techniques? Because in that case, you don't really have, if you're comparing to just end-to-end deep learning, there isn't really a state of the art for safety. Maybe there's conformal inference, but I'm not gonna badmouth conformal, but it has its limitations. And so, you don't have to compete with like end-to-end massive scale deep learning if you can say, hey, I can give you a safety guarantee that none of these other methods is able to give you. And maybe including kind of more methods around the safety certificate certifiability robustness in future work could be a way to kind of like elucidate the unique benefits of this framework as opposed to kind of the more conventional ones.
That's a fair point. And I think hopefully with some of these, especially with the deck MPC stuff, I think the hope would definitely be. I'm not sure if I actually don't know enough about the safety certificates and that line of work, but I imagine at least in the context of MPC layers, the way I was imagining talking about safety would be you have constraints in the problem where if you are able to strictly satisfy those constraints with an optimization problem and observe convergence and satisfiability, I think that was sort of the pitch there. But I do get your broader point, and I do agree with your broader point that I think maybe a little bit more of an emphasis on those aspects of the problem would sort of strengthen some of the pitches here.
And not just in the presentation and in the talks, but even in the remaining research you have left for your PhD, like really zeroing in on what can I do that no one else can, and
right.
And maybe exposing those aspects of the research a bit more.
Right. I think that's a very fair point. I will try to do that. And I think especially, I believe with both of these pieces of work, I think it is possible to do that. And I think it would definitely be worth adding those in and putting the emphasis on those aspects, I think. So yeah, thank you for that. All right. Any other questions?
All right, let's wrap it up.
Stop the recording, please.